So today we're going to talk about Michaelis Menten kinetics in a steady state. But first, let's review the idea that enzymes make reactions go faster, and that we can divide the enzyme's catalysis into two steps. First, the binding of enzyme to substrate, and second, the formation of products. And each of these reactions has its own rate. Let's also review the idea that if we keep the concentration of enzyme constant, then at really high substrate concentrations, we'll hit the maximum speed for a reaction, which we call Vmax. So first, we'll talk about the steady state assumption and what that means. So like I said before, there are two steps to an enzyme's catalysis. Now, when we use the term steady state, what we mean is that we're at a point where the concentration of ES, or enzyme substrate complex, is constant, which means that the formation of ES is equal to the loss or dissociation of ES. Now, notice that I've used equilibrium arrows between these steps, and that was to show the idea that these reactions, like any reaction, can go forwards or backwards. Our enzyme substrate complex doesn't have to form products. It could just as easily dissociate back to an enzyme in a substrate molecule. So I'll call these reverse reactions -1 and -2. If we look at that in terms of our rates, we can say that the rate of formation of ES would be the sum of rate 1 and rate -2, since both of these reactions lead to ES. And the rate of loss of ES is equal to the sum of rates -1 and 2, since both of these lead away from ES. Now also remember that products very rarely go back to reactants, since these reactions are usually thermodynamically stable. So rate -2 is going to be so small in comparison to rate 1 that we can really just cross it out, which means that we can swap out that second double-headed arrow for a single-headed arrow. So using this information, let's do some math. Now I'm going to be deriving a new equation. This can get a bit confusing, so don't worry if you have a little trouble with this. Just rewind the video and try watching it a couple more times if you need to. So I'll start out by drawing the same sequence I did before, with the 3 different reactions. And I'll also write out that steady state equation I mentioned before, where we have rates forming ES equal to rates taking away ES. Now the first thing I'll do is swap out those rate values for their rate constants times the reactants for those reactions. So rate 1 will be equal to K1 times E times S, and so on for the other two. Next, I'll introduce a new idea and say that the total amount of enzyme available, which we'll call ET or E total, is equal to the free enzyme E plus the enzyme bound to substrate, or ES. And using this equation, I'm going to rewrite the E on the left side of our equation as the total E minus the ES, which would be equal to the E we had there before. On the right side of the equation, I've just factored out the common term ES. Next, I'm just going to expand the left side of the equation, so take a moment to look at that. And now what I'm going to do is I'm going to divide both sides of the equation by K1. So K1 will disappear on our left side, and on our right side I've put K1 in with all the other rate constants. Now since all these rate constants are constant values, I'm going to combine them in this expression of K-1 plus K2 over K1 into a new term Km, which I'm going to talk a little bit more about later. So in this next line, I've done two things. First, I've thrown in that Km value that I just mentioned, but I've also added ES times S to both sides of the equations, and thus moved it from the left side to the right. In the next line, I've done two things. First, I switched the left sides and right sides of the equation, just to keep things clear, but I've also factored out the common term ES on our new left side. And then what I'm going to do is I'm going to divide both sides of the equation by Km plus S. So I can move that term to the right side. So I'll make some more room over here, and now what I'm going to do is remind you that the speed of our whole process, which I'll call VO, is equal to the rate of formation of our product, which we called rate 2 before, which is also equal to K2 times ES. So now using our equation over here, I'm going to multiply both sides of the equation by K2. Now here's where it gets really tricky. Remember that if we're at our max speed, so a reaction speed VO is equal to Vmax, which happens when our substrate concentration is really high, then our total enzyme concentration is going to be equal to ES, since all of our enzyme is saturated by substrate, and there won't be any free enzyme left. So K2 times ET instead of times ES would be equal to Vmax instead of being equal to VO, like you see at the top. So I'll make some room here and then sub in K2ES for VO and K2E total for Vmax, and then we finally get to our end equation, which is called the Michaelis Menten equation and is super important when we talk about enzyme kinetics. So let's take a few steps back and talk about the Michaelis constant. So first, I'll write out the Michaelis Menten equation, and if you remember, we created this new term which I called Km, but we never really talked about what it meant, so let's get to that. Now, if you bear with me for a moment and pretend that Km is equal to our substrate concentration, then we can sub in that value into our Michaelis Menten equation, which would put 2s on the bottom, the sum of s plus s, and then the s will cancel out, and we'll be left with Vmax over 2. And what this means is that Km, which we call the Michaelis constant, is defined as the concentration of substrate at which our reaction speed is half of the Vmax. So when VO is equal to 1/2 of Vmax. And if we look at that on a graph from before, you'd see that Km is a substrate concentration specific to our circumstances, where our rate is at half of its max. And the lower our Km, the better our enzyme is at working when substrate concentrations are small. And we can use this Km term to quantify an enzyme's ability to catalyze reactions, which we call catalytic efficiency. So I'll rewrite the Michaelis Menten equation. Remember, we defined Km as a substrate concentration where VO is 1/2 Vmax. And since it's a concentration, it will be in units of molar, or moles per liter. But now I'm going to throw a new term at you called Kcat, which is equal to the maximum speed of a reaction divided by the total enzyme available. And we call this the enzyme's turnover number. And all this term is how many substrates an enzyme can turn into product in 1 second at its maximum speed. And we measure it in units of seconds to this -1, or per second, as in reactions per second. So we can define an enzyme's catalytic efficiency as a combination of Km and Kcat. And we do this by saying it's equal to Kcat over Km. So a higher Kcat or a lower Km would result in an increase in an enzyme's catalytic efficiency. And every different enzyme has a different catalytic efficiency in certain conditions. And we can use this term to score enzymes on how good they are. So we covered a lot of content in this video, but the really crucial points to remember are first, the idea of the steady state assumption that we make when looking at enzyme kinetics. And this is where we assume that the ES concentration is constant, meaning that the formation and loss of ES are equal. Second, we derived the critically important Michaelis Menten equation, which you should consider committing to memory. And third, we talked about how you can score how good an enzyme is at speeding up reactions by looking at that enzyme's catalytic efficiency, which is a combination of two new terms we learned about, Kcat and Km.